So after this panel discussion, we directly go on with the next keynote. And the next keynote is being presented from Leon Stolpmann. Leon Stolpmann is quantum computing lead for Adesso, Schweiz, and he's talking about security of quantum machine learning systems. Leon, the stage is yours. You're also joined by your colleague. Didn't know that. Also happy to introduce Jeanette, Miriam, the colleague from Fraunhofer IKS. Stage is yours.
Okay, so you obviously have not the latest instructions, but we will do that.
Welcome everyone to our talk on the security of quantum machine learning systems. We're presenting here today as a conglomerate, myself from Adesso and myself, I'm the quantum computing lead for Adesso Switzerland, as well as Jeanette, who is the head of the department for quantum enhanced AI at Fraunhofer Institute for Cognitive Systems, and also Daniel from Quantagonia, who isn't here today, unfortunately, but who was instrumental in the development of some of these ideas, which we'll be presenting today. In particular, we've got 4 topics today. Firstly, we'll introduce quantum machine learning. What is it? Why should we care? And show you some examples. Secondly, we'll talk about security in classical machine learning, as that forms the foundation for this new field of quantum machine learning security. And finally, we'll offer some proposals and directions for future research. Starting with, why should we care about quantum computing and quantum machine learning in particular? Well, I probably don't need to explain it to you since you took the time to come to this conference, but let me try to offer an explanation nonetheless. Fundamentally, quantum computing is about matrix operations and about sparse matrix math in particular. And that's a fundamental underlying mathematical paradigm for some key computational problems which we see across industry. So many of them have been mentioned today. We've got simulation of chemical systems for drug development. We've got optimization for finance and insurance and logistics. We've got cryptography, and Shor's algorithm was mentioned a couple of times today already. And finally, we've got machine learning and quantum machine learning, which we are talking about today. And looking at quantum machine learning or machine learning in general, we can establish 2 types of classification dimensions to narrow down what we're talking about. On the one hand, we've got which type of data is used, so is the data classical or quantum? And secondly, we've got how the computation is actually done, classically or quantum mechanically. So on the top left here, we've got classical machine learning on classical data, which is being discussed over there. And on the bottom left, we've got classical machine learning for quantum data, which is hard due to the high dimensionality that we see in quantum computing. On the bottom right, we have quantum for quantum, so I apologize for the slight mistake in the slide there. But this is in the future, using quantum data directly to feed quantum machine learning systems. And the top right is where we are today. That's using classical data in quantum machine learning. And that breaks down either into 2 approaches. So either we use some quantum machine learning subroutine in our classical pipeline, or we try to approximate the classical operation with a quantum variant altogether. So let us go into a little bit more detail. What we have is, inspired by the classical methods which we've seen, we can establish 7 main types of methods that are used in quantum machine learning. So firstly, we've got clustering, which benefits from the inherent high dimensionality that we see. Secondly, we've got classification, which is advantageous because we can do inner products very well natively on quantum computers. Leading, of course, or we've got support vector machines due to the inner products, which then support, of course, quantum classification tasks. And we can talk about 2 applications of finding eigenvalues and eigenvectors, so we can do principal component analysis and establish feature topologies. And finally, we've got quantum neural networks, which enable us then to do quantum deep learning and quantum reinforcement learning as well. And if we go into a little bit more detail, we see that these methods are supported by the quantum algorithms, which we all know and love. So wherever we've got optimizations that need to take place, we can in principle use quantum annealing. So that would support clustering and SVMs and classification, as well as subroutines for neural nets. And we've got quantum kernel methods, which have been very prominent lately and which were mentioned earlier today as well. These are, of course, used in support vector machines and classification. And anywhere where we need to find eigenvectors, eigenvalues, we can use the HHL algorithm for solving systems of linear equations or also matrix inversion. And underlying all of it, we've got our equivalents of the basic linear algebra subroutines, which are the quantum basic linear algebra subroutines. So there you find your familiar algorithms such as the Fourier quantum QFT, quantum Fourier transform, phase estimation, and then we have a whole zoo of hybrid algorithms which draw on these fundamental algorithms and have some classical component as well. Since you have some background now of what we're doing, I think it would make sense to have a look at an example for you to see what that would look like in practice, and I would like to hand it over to Jeanette.
Yeah, exactly. We thought at that point it would be very useful if we really make it a little bit more practical after this kind of theoretical introduction. And so before we are getting to our example, let's zoom once again in what a quantum machine learning algorithm is. So what you see here on the top is exactly what you would do now in classical machine learning. You have some kind of data set, then you have run some kind of machine learning algorithm, and then you get some prediction out. In principle, for quantum machine learning, we are doing just the same, but we have two additional steps. The one step is that we also need to encode the data. We need to take the classical data and need to transform it into quantum data before the quantum computer can run some quantum machine learning algorithm. And then we need to do the same step backwards. We need to do a measurement, convert the quantum data back into classical data. So, and now, having said that, our example. Here we are looking at the classification of medical images. So the task that we would like to look at here is there anything in these kind of medical images, ultrasound images on the top, CT images on the bottom, that we should worry about. So is there anything that you should call the doctor? And this is in principle a task where we would also love to use classical AI. That's very difficult at the moment because here we have a very limited amount of training data, and we have good hope that quantum enhanced machine learning algorithm will be very helpful. And that is because this algorithm is promised to work better in the situations where we have very limited training data available. To hint you, the solution on how we could do that is essentially that we take a convolutional neural network, like you know it from classical machine learning. We are taking one convolutional layer, we are replacing that by a quantum convolutional layer, and then we can essentially extract in a more efficient way the features in the medical image that we are interested in. And as I was saying, for this particular algorithm, we have theoretical indications that it would be more efficient in the case of little training data. Not going here into any kind of details, we just wanted to tease at that. You immediately see from this kind of problem that now we start to think about using quantum machine learning in an application domain where we need to be extremely certain that the result is, on the one hand, robust, and on the other hand, we need to worry about security. So we should make sure that our medical diagnosis is correct and does not get disturbed. And this, in fact, then brings us to the question of security of quantum machine learning. But before we do that, we first review the classical security of machine learning.
Indeed. The field of classical AI security, of course, is the foundation of looking into security of quantum machine learning systems. And there, we need to think about what is the attack surface, what can be attacked, and how can it be attacked. So the attack surface is in principle any component along the life cycle. So these systems are firstly specified, the data is gathered, and then the data is prepared, leading into the implementation of the overall system, the selection of the model, the evaluation of the model, and finally the clearance and the model deployment. And along this life cycle, we have three main risks or attack vectors which are applicable at any point. So firstly, we could have a compromise of any of our subcomponents, like a vulnerability in a library. There was recently a pretty bad vulnerability in the LangChain library, which is used in NLP. We could also face the threat of data poisoning, either during the collection or during the preparation. Or we could have a privacy attack where the model or the data is disclosed in some type of way. And once the model goes live, we need to worry about, well, failure or malfunction of our application components, for example, due to a denial of service attack. And we need to worry about adversarial attacks. So oracle attacks where people try to query the model in a repeated and systematic way to gain some access to confidential information or of the data or the model itself by searching then the problem space of what they find. Or we could think about adversarial, like classic adversarial evasion attacks where the system is driven to act in some unintended way by adding an imperceptible adversarial perturbation. So what about quantum machine learning? Do we still need to worry about these vectors? Are we safe? And the answer is, of course, no, we're not. The life cycle basically follows at a high level the same structure, though there are some particular substeps which are only found in quantum machine learning, like the encoding. But in principle, since we're dealing with classical data, it could still be poisoned at any point. Any of our classical or quantum subroutines could be compromised. For example, if you think about third-party compilers, which are used a lot of the time, or optimizers for optimizing circuit depth, those could contain vulnerabilities, intentional or unintentional. And we also still need to worry about privacy attacks because, for example, for Kubo formulations, those are in principle reversible. So if you analyze traffic about them, you could try to invert the problem formulation. And finally, once the model is live, we still have the threats of adversarial attacks, and that's been a hot topic lately. And a lot of research has been done in the recent past. So I'd like to hand over to Jeanette to show you an example of that.
So, again, turning to the example that we had previously, what would now happen if you start to insert some very carefully crafted perturbation? So invisible to the human eye, some attacker is kind of overlaying that to the algorithm that we have seen earlier. And suddenly, you get a completely different outcome. So the picture is not classified as benign anymore, but you get the output of malign in this particular case. So the doctor would now take action incorrectly. And in fact, studies have shown that these kind of classical attack vectors are highly relevant for quantum machine learning as well, and this regardless if we are talking about black box attacks or white box attacks. However, interestingly, you still need to have this carefully crafted attacks. The very same study has also shown if you're just adding randomly noise, then you see in fact that things are more robust. Of course, when you're then going to protect the algorithms in terms of this attack, then you would think about an adversarial training. But this is essentially now just taking the classical attack vectors. Now the question, of course, arises, are there also new attack vectors that we need to worry about? And indeed, because as I was outlining earlier, we have now additional steps in quantum machine learning. One of the steps is in fact the encoding, so the transformation from the classical data to the quantum data. The other step that we did not yet spoke about is that we also have noise. So we are speaking about noisy quantum computers. And if we are now zooming in both of the components, then in fact the encoding is very relevant to obtain quantum advantage. So if you're starting to attack that or disturb that, then you may completely lose the quantum advantage, in fact. Similarly for the noise. So zooming in on some kind of examples, for the encoding, what could, for example, happen is that an attacker starts to insert additional gates. So you do the encoding by applying a couple of gates that take, for example, the data as parameter in. Now the attacker could just insert additional gates surrounding that, and then you could disturb the encoding that much that you are losing the quantum advantage. There are, however, then also other studies in literatures, like randomized encodings, that propose methods to make exactly this encoding step more robust. In terms of noise, similar issue. So we have here two lines that we would like to highlight here, and both are very interesting, in particular for the future when we are speaking about bigger quantum computers. The one is about crosstalk, and crosstalk is now a very technical term. I will also outline that on the next slide in a little bit more detail. The point is that when we are putting more than one circuit on a chip, then these two circuits can disturb each other. A similar thing we can play when we are looking at specifically ion trap hardware, in the case that more than one ion trap is present, because then it can happen that qubits are shared between the different traps, and these can disturb each other. So looking at this here in a little bit more detail, this is the first example that we talked about this crosstalk. And what would happen is that you see here on the top, you have essentially the circuit that you really would like to execute. And now some attacker is putting some additional circuit on the very same hardware. And because of the crosstalk, that is essentially saying that there is a connection between the various qubits, you get a correlation between both circuits. And therefore, you can disturb the circuit that you, in principle, wanted to execute as user by the attacking circuit. Similarly, for our ion trap system, where an ion is shuttled from one ion trap into another ion trap, then both of the ion traps are correlated, and therefore also an operation of a victim can be disturbed by an attacker. Essentially, depending on how severe the problem is, both attack modes could result in a denial service. And so we would like to conclude with this slide here. Both these components, so the encoding scheme and the noise schemes, are things that are important to consider in the future. They are both harmful because it's new modes to carry out attacks, but in both cases there are also proposals to use that to make things in fact more robust. And therefore we are looking forward to continue working on this research in fact. So, and then we are open for questions.
Thanks a lot for your insights. Do we have any questions already? We have a question over here.
Thank you for your presentation. I have a question regarding, you mentioned while using the quantum approach for medical detection, a smaller database can be used for quantum compared to the classical method. Why is it so? So a data set with 10⁻² to 10⁻³ is enough for quantum classification.
Yeah, that's of course always the question that I get, and there is an easy answer and there is a mathematically involved answer. The easy answer is because quantum neural networks are able to have a higher computational capacity.
Okay.
The complicated answer goes to the curvature of Riemann manifolds.
Okay, so the higher coverage, so the information can be captured more efficiently using a qubit.
Yeah, you can imagine that like the quantum neural network contains more information. Of course, to point that out, we are not inventing information. So
Okay, right.
the information still needs to be within the data, right?
But how do you ensure there's overfitting if we have a lot of features which a qubit can represent?
This can happen. This depends on the algorithm, and
Okay.
there are then various means, yeah.
All right, yeah, thank you.
Do we have another question? Yes, we have one.
So, did you think about hybrid attack vectors, for instance, a classical adversarial attack on a quantum machine or a quantum adversarial attack on a classical machine, and how the differences are?
Yes, and there is in fact a paper about attack transferability, classical to quantum and quantum to classical. And the preliminary result at the moment seems to be, yes, classically found and classical adversarial perturbations can be effective in quantum machine learning systems. And of course, samples that are found for the quantum machine learning systems can transfer to classical systems as well. So there seems to be a transferability in both directions, though there isn't much research on it yet.
Thank you. So I think we don't have any more questions, so it's just for me to say thank you for your very interesting insights. Thanks for your presentation.
Thank
Thank
you.
you.